Thank you very much. So I'm Tim Raymond, and I'm here to talk to you about parsing expression grammars. But before we start talking about that, our story today actually begins back in 2013. And at the time, I was working for a media company, and we had a templating language at the time, which was intended to be very simple. So we had bits of text, and we had pieces of product information that we didn't necessarily know ahead of time. So our editorial folks were writing these articles, and then later on, we'd fill out all of this information. So intended to be very simple, and then later on, we would see a rendered article like this. And we thought, well, this is so simple, we might as well use the simplest thing we can. And at the time, we were writing Ruby, so we thought, hey, let's use regular expressions. They're built into the language. And we can simply do substitutions, and everything will work great. And it did for a while. But the fundamental nature of any business requirement is that it's going to change. So after a while, we started to have requirements like, well, wouldn't it be nice if we could have like text rendered some of the time? Or, it would be nice to modify some of these replacements, have some options, things like that. And it wasn't long before we realized that we had accidentally created a templating language. And our regular expression-based engine for this became a lumbering monster in our code base. So it was around this time that I saw this talk by Rob Pike, which is all about the design of the scanner in the text template package. And this talk completely blew my mind at the time. It's still very relevant. It's aged well. I highly recommend it still. And I thought, well, the text template package, this language is actually really very similar to the one that we're working on. And I have the perfect language to try this out on. So the result was great. This project completely sold me on Go because we took this regular expression-based parser, and we ended up reducing rendering times almost 2 orders of magnitude, which was fantastic. If you haven't had this experience of writing a parser by hand, I can't recommend Torsten Ball's books on writing an interpreter in Go and writing a compiler in Go enough. Those resources didn't exist at the time, but they are great. And I recommend trying them out before you try the things that I'm going to show to you today. So this is, parsing expression grammars are the next step that you would take after you've written that first parser and understood that there's really nothing more than code generation going on here for you. And parsing expression grammars, or PEGs for short, give us a way to take the grammar that we would have to write out by hand or in comments and allow us to generate code directly from that. So it lets our parser remain very flexible in these early stages. And also, they also remain well documented, and the code that's generated stays aligned with that documentation. So to show you how PEGs work, we're going to take a look at parsing the go.mod file that was introduced in Go 1.11. This is a new file format, and this is the simplest go.mod file. It just describes the name of a module and the version of Go that it builds with. So before we start, I like to think about having a good project layout for this. So I usually start with a few different directories. I like to have some kind of a directory for binaries. You usually like to use your parser, so I like to have usually like a functor in there or some kind of a highlighter, just something that I can take arbitrary files, make sure they parse with it. The next package in here is going to be a parse package where our parser will live. And we'll take a look at some of the files that's in that parse package next. The first thing I like to do is have a go generate file where I can put the specific command used to run Pigeon inside a gen.go file. And this is so that way I don't have to remember all of the flags to Pigeon and that sort of thing. Once we have this, we can actually go and download Pigeon using go.get. And that is at github.com/mna/pigeon. And now we can actually start working on our grammar. And this looks a little bit different, but remember, we're generating Go code from this. And this is the simplest PEG file that you can write. And the reason it's the simplest is because this will parse literally anything that you throw at it. So this is broken down into a few different parts. The first part is a code block. And the code block is verbatim Go code that will be pasted into your generated parser. Any Go file has to start with that package statement. So at minimum, you also need to have a package statement within this code block. And those curly braces are what delineates the code block portion of this. The next part is the actual grammar rules. And we have two of them here. The first one is the rule which is the default rule, and it matches the entire file. And what we're saying here is that a mod file is any character 0 or more times followed by an EOF. And you'll notice that it kind of follows something similar to a regular expression, but the rules are a little bit more restricted because we can refer to other rules as well. So EOF is defined as another rule, which is the inverse of any character, which would be the end of the file. So we can then use GoGenerate because we set up GoGenerate before. And once we do that, we will have a parser, and that will generate a parse.go file for us. And if you open this up, it looks like auto-generated code. It's not beautiful, but it works. Tests. I love having tests for my parsers because they're very easy to test. We can just create input files, see if they parse. They don't require any dependencies on things like a database or any third-party connections. Nothing to clean up. They're very easy to test. So I usually like to start with some kind of a test that looks like this, where I use that special test data directory to have samples of things that need to be parsed. And I use the file names from that as the names of subtests that I start. And I'm going to use the parse.parse file function that was generated by Pigeon as a way to open that file, parse it, see if there were any parsing errors, and return an error. So because this parser will parse literally anything, unsurprisingly, that test will pass. But at least we have all of the machinery in place here to build something useful. So at this point, we have to decide, OK, what is this actually going to do? So usually, when you have a parser, the goal here is to create some kind of structure that will be what you're actually working with in your code. And that's sometimes called an abstract syntax tree. Here, we're going to produce just a couple different structs, which will describe the entire file. I'm calling it a manifest here. And it'll also have things like a Go version, where we can maybe compare different versions of different files. So we have to modify our test here, so that way we can make sure that when we parse something, that it produces the correct manifest file. So we just add a little bit to our test. We have now a table-driven test. And we can also modify the body of the test to actually perform that comparison and make sure that our expected manifest file matches what we actually got back. So if we run this, we're going to see that this now fails, which is good because our tests are now helping us drive this parser forward. So to actually produce this manifest file, we can add what Pigeon calls an action block to our rules. So after the definition of the rule, we can put a pair of braces, and this is Go code that will be fired when this rule matches. So all we're going to do, we want to, again, just have the next simplest thing that will work, and we're just going to return exactly what we expect to see in the test. And when we run that test, we're going to see that it passes. So we now have to write a test that will break that assumption that we are using Go 112. So we're going to write another test that uses Go 113. So just very simple change. So when we run this, we see that the test fails, and it fails because it was expecting a different version to be returned. So now we have to do this for real. So what we can do is break up this mod file rule into several constituent pieces. So we'll say now that a mod file is composed of a few different rules. It has a mod name, which is the module name. It has some new lines, and it also has a Go version followed by some more new lines and an EOF. And you'll notice that we can assign variables from the result of those rules. And we can use that as we're building up this struct that we're returning. The definition of these rules is that we have a mod name is the literal string module, followed by a space and a path definition. And a path is a directory name, which you can see down below is just a sequence of characters. It's probably not exactly right for all directories, but it's useful for what we're trying to do here. And also within that path rule, you can have additional slashes followed by more directory names, and that can happen 0 or more times. And we're taking the entire thing that was matched with c.text and returning that as a string. The other bits here we need are a Go version, which is the keyword Go, followed by the version rule. And a version is a few numerics separated by a period. And at each stage, we're just returning a little bit of string or a little bit of struct, so that way the next stage higher can combine those things into a more cohesive whole. It's also pretty common to have some utility rules or primitive rules. We've seen numeric referred to. We can use some standard library things like string convert to convert those strings back into numbers that we can actually use. We also have some things for things like new lines and spaces, and we've already seen EOF. So now that we're actually breaking apart this file, when we run our generate command, we have to regenerate that parser. We can then run our tests, and we see that they all pass. So now we can push this a little bit further. We want to parse dependencies. Ultimately, we want to understand the dependencies of our application. So to do this, we first need a go.mod file that has a dependency, and it will have this require directive here with the name of another module. So our test now includes a dependencies slice here, and we're describing another module's dependencies here. And what we can do is we run go test here, and we see that that will fail because it doesn't know anything about dependencies yet. And we can use the same trick here. First, we're going to modify that mod file rule to say that now a mod file is a module name followed by a Go version followed by multiple dependencies. And we're going to pass that along in the struct. Dependencies here is defined as 0 or more instances of the dep rule. And this is probably my least favorite part of working with Pigeon, is that these variables that are returned to you as empty interfaces. And if you have a rule that could be 0 or more like this, you're going to have to convert that first into a slice of empty interface, and then you have to convert each of those empty interfaces within the slice of empty interfaces into the thing that you actually want. But if you can get through this, then that's really my least favorite part of working with this. But within the dep rule itself, we're just going to match that literal thing that we're looking for because we want to be able to make progress with our tests. And more importantly, this step will tell us if we got all of this parsing logic correctly. So when we run go generate again, and then we also run our tests, we'll see that it passes because it's only looking for that one singular string. Now we want to look at parsing multiple dependencies. So this introduces something interesting from a parsing perspective because we start with a single dependency here. But when you look at what a go.mod file with multiple dependencies looks at, you'll notice that we introduce these parentheses. So we have to treat these a little bit differently. Just like we've been doing all along, we're going to add a new test which has multiple dependencies within it. Then we're going to run that test, make sure that it is a useful test, that it is actually failing. And then we can actually modify this dependencies rule to work with multiple dependencies. So we're going to say that our dependencies rule is now the word require followed by an ordered choice. And pegs have an ordered choice in that this rule here will first try that dep rule, and if it's unable to match a single dependency, it's going to unwind, go back to this point, and then it's going to try the multi-dep rule. So for that single dependency rule, we're going to have now the name of the package. Again, we have to actually do this for real now because we can't just have that literal string. So we're going to break this up into a package, a space, a semver string, and then an optional comment. And we actually don't care what the comment is at this stage. We're not parsing down to that detail. So we only really care that that comment is present. And that's why we're using the traditional OK value as just a detector of whether a Boolean was returned at all. So the individual pieces of this are we have a package, which is, again, a path. We can reuse the rules that we've already defined. And we can also reuse some of the version rules again. This time, we have renamed the version rule to a mage min pat, so it can have 3 different parts to that version. And the only thing new here really is the comment rule, which follows the comment that can appear inside the go.mod file. This is the definition of that mage min pat rule. Again, it's very similar. We just have 3 numerics separated by dots. And when we generate this parser and then we run our tests again, we're going to see that all of these things pass. Now, this isn't the most useful parser in the world because we still have a lot of work to do. We should implement things like the replace directive and the exclude directive. And there's also a few other things that we should address because in the way that we've developed this, we've actually diverged a little bit from the reference implementation. So that would be something else that we could address. But pegs are flexible enough that we could address all of these issues. We could go back, we could modify the grammar, and we're not really too committed to a particular way that we've implemented these things. And the point of this here was that we built a useful parser in about 20 minutes. And this is something that isn't necessarily the realm of academia. If you have some kind of a configuration file or some foreign file format, this is something that you can use as well. And I hope that seeing these tools can help you build the utilities that you need. So thank you very much. And I'm Tim Raymond. I work for Gopher Guides, and you can follow me on Twitter if you have any questions. Thank you.